Hello everybody, we are team number 5 from section 3. My name is Mili and I have the pleasure to introduce to you our AP Coolbox design presentation. Team number 5 has been tasked by a client to create an AP Coolbox. We broke down a complex process into a smaller, more detailed design task. We started analyzing our objective and constraint, then our function and means, followed by a morphological chart, and finally by a comparison table analysis. Let's explain first our objective and constraint. We focus on the client's initial problem statement, and then we revise the problem statement by incorporating the appropriate objective. Then we have our main objective. The box should be produced at low cost, should be environmentally friendly and safe. Then we have secondary objective. The box should be built with durable materials, and those materials has to be recyclable and reusable. The box should open and close without harm. Then we incorporated the constraint that our design must meet. The box should be built with material accessible to the designer, those provided in the M250 course kit. And then the box should open without direct intervention. That is to be self-opening as a person or object approaching. And finally, the box shouldn't have any sharp edges. Now it is time for our designer, Advaith, to continue explaining our design process.
Hey everybody, my name is Advaith. Let's continue talking about the design process. Next, our team created a functions means tree. A function means tree is a diagram used to break down the necessary functions of the project and generate concepts. The function means tree has two different components, the functions, which are in the rectangles, and the means, which are in the rounded bubbles. The function means tree is read from top to bottom, starting with the basic function. Here, the main overall function of the Epic Cool box is that it needs to contain an object, hence why this function is at the very top. In the second level, there are three branches which represent the means by which the basic function can be implemented. Our team came up with a box, jar, and a drawer in order to contain a certain object. Underneath the second level are the secondary functions followed by their means. As you can see, there are elements of the tree that are repeated. For instance, in each of the box, jar, and drawer concepts, one of the secondary functions is to open. All three also use Arduino software as a means to communicate and perform a certain task. One key difference between each is in the way the item opens. The box opens from the top, the jar opens by unscrewing the lid, and the drawer opens using a sliding mechanism. This tree allowed the team to identify the different functions present and define how these functions can be implemented. We concluded that Arduino software would be a crucial part in the design process in order to achieve the primary function. Next, we have Alfred who's going to talk more about our design process.
Thanks, Advaith. So for the morphological chart, we looked at all the different combinations of the functions and means that you had mentioned a bit before, and from there we put them all into an easy-to-use, accessible chart that would allow us to see all the different combinations that we could use for our design in building the Epic Cool box. So after we started doing this, we realized that we had a lot of combinations of functions and means, over 50 different functions and means which we'd be using in order to help solve how to make this design. So we looked at all these designs and made them into a couple main functions that we noticed were similar between all the different designs. Those functions included the containment of the object, the signal communications with the detection between the Arduino and within the Coolbox system, the autonomous opening which will also combine together with the Arduino system, the activation of power which would allow the power delivery, in turn making the box work, and the different materials which included the metals, the glass, or even the cardboard. So from there, we created a reduced morphological chart, which looked at all the different sections and removing all the infeasible sections that we couldn't really use in order to make a really practical design. And we discarded any combinations that violated the design constraints. We came up with a box, a jar, and a drawer, which had similarities in a lot of how their means were taken through with the functions. Eventually, we settled up on the box design, which I'll hand it over to Carlos Bravo to talk about.
Thank you, Alfred. So here I'll talk about the comparison table. As we can see in our objectives is the first column consists of environmentally friendly, low cost, safety, and durability. Each of those criteria besides the cost is out of 5, and then the cost is obviously out of the amount of dollars it costs. So besides the cost, the higher the number, the better. And then for cost, the lower the number, the better. So if you can see, the second to last one consists of the total points. Just the rows out of 5. The box using the photoresistor ended up scoring 13, which was the highest. And it also, as you can see in the last row, was the cheapest to construct at $65. So using the total points and the total cost rows, we were able to come up with the box using the photoresistor as the winner. So for our top concepts, I've got the sketch here made out of cardboard and triggered by the photoresistor. So as we can see here, we have a photoresistor, and when we wave our hand or cover that photoresistor, it'll read a certain reading, which would then trigger the servo motor to rotate. And attached to the servo motor is a rod that will then lift the lid. As we move on to the I should also include that the secure sides here is using tape, so we're taping each side there. As we move on here, we have another one that is made of cardboard. This time it's not using tape, these are actually zip ties, so that's how we secure the sides. And the trigger is a button here, so when you click the button, it triggers a servo motor, and that servo motor is actually on the back plane here, on the outside of it. As we can see, it's attached to the breadboard. The wiring is coming from the back. And basically, when that servo motor rotates, it creates tension in the string, raising the lid. Then finally, we have a spring that lifts it once the ultrasonic sensor here causes the trigger when a hand is between a certain distance. And basically, yeah, and then this one is made out of acrylic, and it's secured on each side using tape. Obviously, your breadboard and your Arduino, just like on the other two concepts. So this is a CAD design. I'm sorry that the numbers are a bit small, but it basically consists of a top view, a front view, a side view, and a back view. Here we have a 12 by 12 by 12 box. So everything is 12 by 12 to create that cubicle sort of box. The breadboard inside is a little over 6 inches, and then the hole in the diameter for the wiring to go through is 1 inch in diameter, and then the rod that does the actual lifting of the box is 8 inches. So here we can see our front view, our side view, and our back view. Here we can see the rod that is sticking out there. And then obviously, as we saw in the previous picture, this is facing towards the front of the box, but as this rotates, it will hit the top lid and pretty much open up the box for us. On the right, we have our breadboard with our photoresistor, and then our breadboard would actually be on the outside of the box. Given that we're using a photoresistor, we're going to cover it, so it would have to be on the outside. We've got our servo motor here, as I mentioned, and then we can see a little bit of the tape here from the top view. That's basically it there for the CAD design, so thank you.